Alright, so I hope I am audible to everyone. So my name is Avik Mukhopadhyay, and as you know, I am one of the TAs for this course on digital signal processing. So today we will be discussing some sample problems in this live session that are related to the contents of week number 9. So if you recall, in week 9 you were introduced to the notion of phase response. Then the all pass filter was discussed, and we also saw the group delay and its physical interpretation, and some comments and remarks were made on the effect of non-linear phase that leads to the wave shape distortion, etc. So keeping these concepts in mind, let's get started with our today's sample problem solving session. Okay, so I hope everyone can see question number 1 on the screen. So in the question, we are given a linear phase discrete time LTI system having a frequency response capital H of e power j omega and a real impulse response h of n. Okay, and as we have seen in the lectures, the group delay for such a system is defined by tau of omega, which is nothing but the negative derivative of the phase of the frequency response. So tau of omega equals to minus t d omega of the phase of the frequency response, and it is assumed that the phase has no discontinuities, and we have been given some information. Okay, the magnitude of the frequency response takes the value 2 at omega equals to pi by 2. Secondly, we have been given that the phase at omega equals to 0 is 0, and the group delay at omega equals to pi by 2 is 2. Now, given this information, we need to find the output of this system for both these given inputs. So in part A, the input is cos of pi by 2 n, and part B is a similar input. So it's a sinusoidal input of the form sin 7 pi by 2 n plus pi by 4. Alright. So in the question, the very first keyword that is noticeable is linear phase. Now, why this linear phase information is important? Because so let's see why this is important. So before that, let me write down the given information. Okay, so I hope everyone has read the question. So let me go to the other tab. Okay, right. So let me quickly check if the recording is going on. Yeah. Okay, we are looking at question number 1. Alright, someone wants to join.
Yeah, good evening, sir.
Yes, good evening. Good evening. All right, so I was about to start. So today we are going to discuss some sample problems from the contents of week 9. And if you remember, in week 9, the notion of phase response was introduced, followed by a discussion on the all pass filter, and we also looked at the group delay and its physical interpretation, and uh, some remarks were made on the nonlinear phase and its effect on the phase, so it causes the wave shape distortion and stuff like that. So keeping these concepts in mind, let us start with today's problem solving session. So yeah, I just had already read out the first question, so I hope you can see the first question. In the first question, we have been given a linear phase discrete time LTI system having a frequency response capital H of e power j omega, and with a real impulse response small h of n. And as we know that the group delay function is given by the negative of the derivative of the phase of the frequency response, so tau of omega equals to minus d omega of the phase of the frequency response, and it is assumed that the phase has no discontinuities. And we have been given with this three information. So the magnitude of the frequency response takes the value 2 at omega equals to pi by 2, and the phase at omega equals to 0 is equal to 0, and the group delay at omega equals to pi by 2 is 2. And given this information, we need to now find the output of this system for both these given inputs. So we are looking at part A, where the input is cos of pi by 2 n. So is the question clear?
Yeah, sir.
Okay, okay. So I will just write it down. Yeah. Alright, so we're looking at the first part. It's a linear phase. Just a second. Okay. So it's a linear phase, discrete time LTI system, and we have the group delay as tau of omega expressed as this, and we also know that it is given that the impulse response is real, and few other information have been given, such as and okay, now we need to find the output when the input is, let's say, x of n is cos pi by 2 n. So this is the thing. So we need to find the output. So we have this input going to our system, we need to find this output. So if you recall the notes while discussing the frequency response of LTI system, this output y of n, whenever we apply an input to an LTI system which is of the form some a cos omega naught n plus phi, it undergoes, okay, this is missing bracket here, okay. So as I was saying, whenever we apply an input of the form a cos omega naught n plus phi to an LTI system, it undergoes two things. Firstly, an amplitude scaling happens, and secondly, it undergoes a phase shift. So the amplitude gets scaled by a factor of the magnitude of the frequency response evaluated at the frequency of the input, and the phase also gets shifted by an amount which is equal to the phase of the frequency response evaluated at the input frequency. So in this case, the input is cos pi by 2 n. So omega naught, if you compare with omega naught n, that form, omega naught is indeed pi by 2. So the input frequency is pi by 2. So firstly, there will be amplitude scaling. So amplitude scaling, the factor of scaling is h of e power j omega, its magnitude at pi by 2. So which is this is the amplitude scaling factor, and the signal will remain the same, which is cos pi by 2 n, and as I also said, it will also undergo a phase shift, and that amount of phase shift is the phase at the input frequency, which is pi by 2. This is the output, and you can stop me or ask me any doubts at any point. So mod of capital H of e power j pi by 2, we already know this, it is given equal to 2. So y of n is 2 times cos pi by 2 n plus this. Okay. Now this factor inside the cos, this phase factor, the phase at pi by 2, see, from the given information we still don't know. The phase has been given at omega equals to 0, it is 0, that's fine, but we don't know its value at omega equals to pi by 2.
Excuse me, sir. Whether it is any formula like that, output y of n is equal to modulus of e power j. Whether it has any formula like that?
Yes. So that's what I was saying. So okay. So in general, if you have, let's say, an input of the form a cos omega naught n plus phi. You feed this to an LTI system with a frequency response capital H of e power j omega. Now what is this actually? This frequency response, as you know, it is a magnitude times this its phase. It's fine. So whenever you feed an input of this form a cos omega naught n plus phi to an LTI system, the output, it is similar to the input only, but it undergoes two things. First is an amplitude scaling, and that scaling factor is the magnitude at the input frequency. See, the input frequency is omega naught, so at omega naught the magnitude response is evaluated times the input signal remains the same plus phi, and also there will be another phase shift. That phase shift is equal to e power j omega naught. This is the thing. So this is the amplitude scaling, and this is the phase shifting. Now you just see this given input cos pi by 2 n, it's exactly of this form. So here omega naught is pi by 2, capital A is 1 basically, and phi is 0. So I just use this thing. It was already discussed in the lectures, so we can directly write the output as this. Is it fine?
Okay, I understood.
Alright, so we arrived at this y of n is 2 times cos pi by 2 n plus this phase at pi by 2. Now we still don't know yet about this value, the phase at pi by 2. So if you go back to the question, I have already actually noted down in here. So there is an important keyword, linear phase. Now linear phase, if you again go back to your notes, linear phase implies that the group delay would be constant, because of course it's for the group delay we are taking the derivative of the phase, correct? So if the phase is linear, then of course the group delay will be a constant. Now regarding the group delay, we have been already given that the tau of pi by 2 is equals to 2. The group delay at pi by 2 is equals to 2. But we already concluded, because of linear phase, that the group delay should be constant. So tau of omega in general should be equal to this tau of pi by 2, which is 2. It should be 2 for all omega, right? So now since we have tau of omega, and we have this relation between tau of omega and the phase of the frequency response, and we also have another additional information that the phase at omega equals to 0 is equal to 0, we can actually now find the expression for the phase of the frequency response. So I am writing it step by step, and again, like I said, stop me at any point. So in the question it was mentioned that linear phase. Now linear phase, it's a linear phase system, which implies that group delay should be constant. So basically you can think like practically the group delay constant, meaning that all the frequency components get delayed by the same equal amount, like that. So let's go to the next page. Now group delay is constant, so we know one value of the group delay, which is tau of pi by 2, which is equal to 2, and that should be constant for all omega, right? So we have the group delay is actually equal to 2 for all omega. This value at pi by 2 is enough for us to conclude this. Now tau of omega is minus d omega of the phase. Okay, I think someone wants to join. Okay. Okay, just to quickly summarize what we have done so far is that we are discussing this first question, in which we are given a linear phase discrete time LTI system with a frequency response capital H of e power j omega, and it is given that the impulse response is also real impulse response, small h of n, and this group delay, as been mentioned in the lectures, is given by this negative derivative of the phase of the frequency response, and we have been given with these three conditions here. Firstly, the magnitude is equal to 2 at omega equals to pi by 2, and the phase of the frequency response is equals to 0 at omega equals to 0, and the group delay at pi by 2 is equal to 2. Given this information, we need to find the output of this system for these given inputs. So we are looking at part A, where the input is cos pi by 2n. So we have started from here. Okay, so the very first information that was given, the keyword was linear phase. So I have underlined it here by red color. So why that is important will be seen now. So in general, whenever you have an input of the form A cos omega naught n plus phi fed to an LTI system with frequency response capital H of e power j omega, the output undergoes two things: amplitude scaling and phase shifting, and the output is given by this. Okay, this is already been discussed in the recorded lectures. Just go through it in case you can't recall it. And in this example, exactly the input is of this form, cos pi by 2 n, and we have used this known formula, and so y of n turns out to be 2 cos pi by 2 n plus the phase at omega equals to pi by 2, this thing. So this is the expression for y of n that we get, but still we don't know the value of this phase of the frequency response at omega equals to pi by 2. Now this is where I was saying that this keyword linear phase will come into the picture. Now group delay, as you know, is the negative derivative of the phase. Now if the phase is linear, then its derivative will be constant. So the group delay is constant for a linear phase system, and the group delay at omega equals to pi by 2 is equal to 2, that is given. Now that should be constant, right? The group delay we just now concluded that it's constant. So for all omega it should be equal to 2 only. So that's what we are writing here. So tau of omega is actually equal to 2, which is tau of pi by 2, and since tau of omega is minus dt omega of this phase, we can write that this tau of omega equals to minus dt omega of the phase. So, or we can write like this. So we have this, and now how can we find C? So just look at this given information. So we obtain that the phase is equal to minus 2 omega plus C. C is an arbitrary constant. So from this three given information, which one can we use to find this constant C? The first one is related to the magnitude, which we don't need right now. Second one is this phase at 0 equals to 0, and third one is already we have used it. So clearly the second one. So the phase at omega equals to 0 is equal to 0. It is given. So let's just use that fact. So we have been given that the phase at omega equals to 0 is 0. So if we just put omega equals to 0 in this above equation, minus 2 omega plus C, so we will get, what do we get? What do we get, C? Tell me.
2 omega.
No, I'm
equal to 0, sir.
Yes. C equals to 0. Very good. So what we are doing is
we are equating to 0. I hope so.
Yes.
Derived value equal to 0. Am I correct?
Correct. So we are putting omega equals to 0 on both sides of this equation, right?
So you are substituting omega is equal to 0.
Correct. So therefore, if C is 0, we can conclude that this phase is actually minus 2. Okay, great. Now we know about the phase. We have complete information about the phase. That's enough. That's enough for us, because we just need to find this, the phase at omega equals to pi by 2, to get the output. So just put omega equals to pi by 2 here now. So h of j pi by 2 is minus 2 times pi by 2, which is minus pi, and you just put this value in the expression of y of n, which is this 2 times cos pi by 2 n plus this actual value that we got. So if you do that, you get 2 cos pi by 2 n minus pi. Okay, so it's just that it undergoes an amplitude scaling as well as a phase shift of pi. So this is the final value, and if you can further actually simplify it and also express it in this form, anything is fine. And now let's go to the second part. I hope the first part is clear. Second part also follows similar. So let me go back to the second part. In second part also we have similar input, right? Sine of 7 pi by 2 n plus pi by 4, and it's true for cos and sine. The same thing follows. Okay, so here we have this. Okay, now this is 7 pi by 2 n plus pi by 4. So the input frequency is 7 pi by 4. So which is our, if we compare with that omega naught n plus 5 form, omega naught is 7 pi by 2. Now in general we know that the output is given by this. First, the amplitude scaling, that factor is given by the magnitude response at omega naught. So our omega naught in part B is 7 pi by 2. So that amplitude scaling factor will be mod of capital H of e power j 7 pi by 2. Now, do we know that value? We only know the magnitude at pi by 2. We don't know the magnitude at 7 pi by 2. See, from the given information, we can't see any 7 pi by 2. We don't know the magnitude response at 7 pi by 2. So, we can't directly write the output for this given input when the frequency is 7 pi by 2. Okay, but we know the magnitude at pi by 2. So the first thing that comes to your mind is how can I somehow convert this 7 pi by 2 thing to some pi by 2. So if I have to go from, let's say, 7 pi by 2 n to some pi by 2 n, I can do that. So I can play with this and I can go to that desired form. So the remark here, what I just said now, we can't directly use 7 pi by 2 because we don't know the value of this magnitude at 7 pi by 2. That is the catch. So like I was saying, so the advantage with all the sine and cosine terms is that you can play with this factor inside this argument. So you can add multiples of 2 pi and stuff like that, right? So we will just do the same thing here. Okay, so remember, we want to have something of the form pi by 2n, not 7 pi by 2n. So I can write it as 4 pi n minus this plus this. So 4 pi n minus pi by 2n is nothing but 7 pi by 2n. Now see, I have found one factor which involves pi by 2n. Okay, good. So now, okay, let me further write this. Stop me at any step if you are not clear, and if it is not clear why I am writing like this. I have written in red the logic why I am doing this. So this can be written. Now you can use this sin A minus B formula. So that is sin A cos B minus cos A sin B. Okay. So if you do that, first term is sin A cos B. So sin 4 pi n times cos of this pi by 2 n minus pi by 4. So what is sine of 4 pi n? Okay, we are expanding this using sin A minus B formula. So the first term will be this times cos pi by 2n minus pi by 4. Okay, and then we have minus cos A sin B. So this. Now tell me, now I am asking what happens to the first term. What happens to this term? Sin 4 pi n. This way you can make a guess. It's all right. Just participate.
We're asking the value of sin 4 pi, sir.
No, I am asking what's the value of sin 4 pi n?
It will be 1.
1.
Is it 1?
Okay.
Sin 360 will be 0. 0. The multiples of 2n will be 0.
So this term is actually 0. In general, sine of any multiple of pi, that is 0. So when m is an integer, so any integer multiple of pi, sine of that angle is pi. You consider sine pi. For m equals to 0, sine 0 is 0. For m equals to 1, sine pi is 0. For m equals to 2, sine 2 pi is 0. And similarly on the negative side also. Correct. So I hope this is clear. Okay, so this first term vanishes clearly. Fine. Now tell me what happens to this term, cos 4 pi n.
Cos value will be for 360, 180 minus 1 plus 1. Again, plus 1 it will be 1.
Yes, plus 1. This is plus 1. Because this is an even multiple of pi. So, cos of any even multiple of pi. So, 4n pi. We have 4n pi and 4n is an even number. So, if you vary n, 4n turns out to be an even number. So, we have an even multiple of pi. You consider cos 0, that's 1. You consider cos 2 pi, that is 1. You consider cos 4 pi, that is 1. Okay, but for odd multiples, cos is negative, right? Negative 1. So anyways, so this is 1. So if you just put these values, you get this as minus sine pi by 2n minus pi by 4. Okay, this is the thing. Okay, Right. Now we have expressed this input. See, the input initially had this frequency 7 pi by 2. Now we have converted it in this pi by 2 form. So now we are fine. Now we can directly use this amplitude scaling and phase shifting formula, right? Because we know the magnitude at pi by 2. Okay. So now we can do that. So therefore output is given by y of n equals, remember there is a negative sign in front, so we will keep it as it is. Now the amplitude scaling factor is what? This. The frequency now is pi by 2, so the magnitude evaluated at pi by 2 is the amplitude scaling factor times the normal signal as it is, and also there will be the phase shifting factor, which is again the phase at the given frequency, which is pi by 2. Okay. All right. So now you know this magnitude at pi by 2, so which was 2, I think. Yes. So this magnitude was 2. So we will put 2 here. And the phase at pi by 2 we already calculated for the previous question. See, the phase at pi by 2, since it is minus 2 omega, so minus 2 times pi by 2, it is minus pi. So if you just substitute these values here, you will get y of n equals minus 2 sine pi by 2n minus pi by 4 minus pi. So this is minus 2 times sine pi by 2n okay. So now what I have done is basically written it like this. Why I can write it like this? Because in general sine of theta minus pi is minus sine theta. Okay.
Sir, excuse me, sir.
Yes.
You have put an minus pi over there, no, for modulus angle of h of e power j omega. Whether I'm correct?
Which one?
You have written no minus 2. That expression,
Yes,
last expression you wrote.
yes.
Minus 2 pi by 2n minus pi by 4 is a given question there.
Yes.
You are given a group delay. That is a delay. That is angle. No, actually they given pi by 2. Where I'm correct in the question?
This third you are mentioning, tau of pi by 2.
Tau of pi by 2 is 2.
Yes.
You in the expression they given as two. I can't get it. Okay, let it be, sir. Angle of h of e power j omega they given in the formula. What you wrote there, no, in the previous step of that you show written as minus pi.
Yes.
Previous step, sir. Previous step. Here, h of e power, h of angle of h of e power pi by 2.
Correct.
You have written minus pi there, no? How it is?
Oh, how I have got this as minus pi. Okay, in the
Yeah, that's what I'm asking.
In the previous part, if you see, in part A, we calculated this expression for the phase minus 2 omega. Remember?
So it's a continuation of that one.
It's the same question only. Just in the two cases, the inputs are separate. We need to find the output.
Okay, sir.
The
I get it.
The system is the same. Okay.
Sorry for this.
Okay, so then minus 2 omega, we just put omega equals to pi by 2 and we got minus pi. Okay. So now again from this step to this step, I use this relation of sign, did one manipulation, and so this minus becomes again minus, which leads to plus, and that's it. So now you can, anyways, you can keep the answer in this form only. You already have the output, but this is just some simple algebraic manipulation. So now what I will do is this. So this, see, here the frequency is like 2 pi by 2, and in our question the frequency was 7 pi by 2. Now if I, let's say, want to express the final output with the frequency equal to that of the input, so if I want to also have this 7 pi by 2 frequency in the output also, like the input, so that's my goal. So if I want to do that, then I can write this as minus 2 sine 7 pi by 2 n plus pi by 4. So how we got this? So you see the fact, we started with x of n equals to sine 7 pi by 2 n plus pi by 4. Okay, this is same as we found that equal to minus sine pi by 2 n minus pi by 4. So I have used this relation here. So now we are going from this pi by 2 to 7 pi by 4. So again adjusting a negative sign, and this minus pi by 4 becomes plus pi by 4. That's it. So, and again if I use let's say if I want to get rid of this negative sign in front, what I can do is again subtract pi, again using that sine theta minus pi equals minus sine theta. So what you get is 2 sine 7 pi by 2 n minus 3 pi by 4. Now this is exactly of the form of the input. The input in part B was sine 7 pi by 2 n plus pi by 4. So we got the output in a similar form, just with an amplitude scaling factor of 2 and a phase shift. Okay, so this is the output. So this is end of question number 1. Shall we proceed to the next question?
Once again, tell me the last 2 steps, sir.
Yes, last 2 steps. Okay, you mean
that is, you have told that minus sine 7 pi by 2 is equivalent plus pi by 4 is equivalent to that is the previous step, 2 sine pi by n by 3 by 4. So the next step you have given us, so in order to change that to sine theta, you have added minus pi, sir.
so you are having doubt in this to this, or which one?
The last but one,
This one.
that you have given minus pi, right? 2
2
sine 7 pi by 4 plus pi by 4 minus pi.
Yes, this step.
Yeah.
So I have just subtracted pi. So you see,
In order, okay.
so previously inside the phase, in the previous step it was 7 pi by 2 like this, 7 pi by 2 n plus pi by 4.
Yes,
In the next step, all I have done is I have subtracted pi. So if you subtract pi, so sine of theta minus pi becomes minus.
In order to have that formula, we have taken minus pi.
Yeah. So I just wanted to get rid of this negative sign. That's why I just subtracted pi. You can leave it in the any form. That's fine. These are just simple algebraic manipulations. That's it.
Okay, sir.
Okay. So yeah. Okay. Good. So let's then move to the second question. All right, so we have been given a non-recursive filter with an impulse response. So impulse response means this is small h of n. This is our small h of n shown in figure 1, and we have been asked what is the group delay for this filter. Okay, what is tau of omega, which is the negative derivative of the phase response. Okay, so this is the thing. Okay, now you don't need to worry about non-recursive filter, that's just a term used here, nothing to do with how we solve the problem. So non-recursive means usually when we have a feedback, when the output, let's say the delayed output is again fed back to the system. So the output, let's say, has a term y of n equals to sum of, let's say, x of n plus x of n minus 1 plus y of n minus 1, like that. So these are recursive systems. We have seen these when sir discussed the recursive implementation of FIR filters. So anyways, but this is a non-recursive system, so it won't involve any feedback term like y of n minus 1. So anyways, so this is h of n, and h of n is non-zero from 0 to 4. Okay, we need to find tau of omega. Okay, so what's the standard process that first, like the standard approach that first comes to your mind for solving this? So we know h of n is given, small h of n, and we need to find this tau of omega. Tau of omega is this minus d omega of the phase of the frequency response, capital H of e power j omega. How can we do this? The standard approach, what is it?
You can find the Z transform, sir. So
Yeah, we can find the Z transform, or since we are dealing with this frequency e power j omega, so we can
substitute that.
we can directly form the DTFT. So this is what is given here is, okay, I think I can't write on this, sorry. Okay, so we are discussing question number 2. Let me draw it for you. Okay, okay, 0, 1, 2, 3, 4. This amplitude is 1, 2, 3. This is 2. This is 1, and this is our given impulse response, small h of n. Small h of n we know. We need to find this, the group D, and we know that the group delay is given by the negative derivative of the phase of the frequency response. Okay, so the first thing that comes to our mind is like you told, first find its DTFT from h of n to capital H of e power j omega. Then we can take the phase, then find the phase of that frequency response, and basically calculate tau of omega. Okay, by taking the negative derivative. Okay, so but unfortunately this is fine. So if you go by this procedure, so it will be a bit difficult to solve in this fashion. Why? Because let's say you solve it, calculate the DTFT. First find this using our standard formula. So here only the samples are present from 0 to 4, right? Small n equals to 0 to 4, and the formula is h of n e power minus j. This is minus, and if you expand it, you will get like this. Now this is a capital H of e power j omega, the frequency response. Now if you have to, the next step would be to compute the phase, its phase. Now if we try to compute the phase, wouldn't it be a very big expression? Of course you can simplify it, but that simplification won't be observable straight away. So because there are so many terms, see, usually what we do for taking the phase is the tan inverse, right? Tan inverse the imaginary part by the real part. But here you see it has 4 complex exponentials, and each of these complex exponential will have a real part and an imaginary part. So there will be cos omega, cos 2 omega, cos 3 omega, cos 4 omega. Similarly sin omega, sin 2 omega, sin 3 omega, sin 4 omega. And even if you find the expression for that phase by writing in the tan inverse form, after that you have to take its derivative to find the tau of omega. So that will be too much complicated, you see. So it is difficult. Calculate the phase and the group delay. In this way. Okay, so rather what we will do is we will try to avoid all these big calculations. So now see, there is a particular pattern in this impulse response diagram, right? So it rises up, reaches a maximum, and then uniformly falls down. So it involves a symmetry. There is a symmetry in this impulse response shape. And what kind of symmetry is there in this h of n impulse response? What kind of function is this?
Even function, sir.
Very good. So this is an even symmetric function, but the only catch is that it is lying between 0 to 4. So in even functions, basically it has to be even about the
Yes, there is, sir.
vertical
About the
axis,
origin.
about
Yeah.
the origin, yes. So but this is even symmetric about n equals to 2. So if so, our only what we can do is we can shift this signal. If we can shift this signal by 2 samples to the left, then basically our n equals to 2 point about which this symmetricity exists will move to n equals to 0, the origin. Correct? So let's try to do that. Why we are doing that, that will be clear. Okay. So far is it clear what I have said? This one okay, all right. So what I said is, we can observe that I am using a different name now, h1 of n, okay, which is nothing but a shifted version of the previous actual original impulse response, shift of 2 samples to the left. Okay, now this, why we are doing this, because this h1 of n would be real and even, okay. So it is already real valued, h of n is already real valued. You see, within 0 to 4 it takes these real values 1 2 3 2 1 and remaining it is 0. So it's a real valued impulse response clearly, and now by shifting it to 2 samples to the left, we already had it real valued, and now we also have it as an even function. So h1 of n is real as well as even, okay, and it will look kind of like this. Is the same thing, only then we have zeros. Okay, so now it is symmetric about 0. And these amplitudes are like this. This is our h1 of n. Okay, now h1 of n is real and even. Can you comment on the Fourier transform of h1 of n? If the time domain sequence is real and even, what is its, like, what nature does its Fourier transform have? Any guess? Anyone can make a case. Come on.
If it is a sine function, we'll be having a rectangular curve. But here we don't have such kind of.
Yeah, that is true. That's like if we have a sinc function in the time domain, we have a rectangular pulse in the frequency domain, and vice versa. So that's a dual pair. But what I am asking is, like, if we have a time domain sequence which is like the impulse response here, h1 of n, if it is real and even, we know that it is real and even. So can we say anything about its Fourier transform? Let's say if we are denoting its Fourier transform by capital H1 of e power j omega, can we say anything like that for the Fourier transform as well? Whether it will be even, whether it will be real, so like that. So it turns out that, okay, I'm writing it. So if the time domain sequence is real and even, it is true that its Fourier transform is also real and even. Okay, so the Fourier transform of small h1 of n is denoted by capital H1 of e power j omega. Okay, so So this of small h1 of n, the Fourier transform of this, is also real and even. Okay. So now if you are not convinced with this, let me show you why this is true. So this is aside, okay, this is just, or let me use, what should I say, this is just a rough. So let's convince ourselves that this is true. The Fourier transform of a real and even signal is also real and even. That's what we want to show. So let's say we have a signal x of n. So let x of n be real and even. Now its DTFT, which is this, which is the Fourier transform, the discrete time Fourier transform, is, you know that it is given by this. Okay. Now I can further write it like this. Correct. Now x of n is even in our assumption. Let x of n be real and even. Fine. Cos of omega n, cos function we already know is even. Now product of two even functions is also even. So overall even. Good. Now let's see for the second term. So x of n, okay, x of n is even by our assumption. Sin x or sin omega n, whatever, it is odd. Now what is the product of an even and odd signal? Yes, what is the product of an even and odd function? Is it an even function or an odd function?
It's odd.
Yes. Yes, is odd. It is odd. And now you see okay, so this whole thing this whole term, why is it not okay? This whole term is an odd function, the product. Now whenever an odd function is summed over from minus infinity to infinity, it becomes 0. Yes or no? So the summation of an odd function is 0 from minus infinity to infinity, because you know, right, it's odd symmetry. So let's see if on the positive side it is of this form, on the negative side it will be of this form. So exactly equal and opposite, so it will cancel out, right? So this is for an odd function. So that's why this second term being summed over minus infinity to infinity, so that will vanish. So we are only left with the first term, which is x of n times cos of omega n. And now x of n is also by assumption a real function, right? It is real valued. See, let x of n be real. We started with this assumption. So this is real, and cos of omega n also takes real values between -1 to 1. So this product is also real, and sum of these products is also real value. So of course, so it turns out that it is real valued as well as it's an even function. Okay, because only this term is prevailing, which is an even function, sum of even functions. So that's why we are making this remark that the Fourier transform of a real and even signal is also real and even. I hope this is clear. Okay, so let us continue. Make a line here. Okay, so now so if this Fourier transform, which is h1 of e power j omega, is real, if the Fourier transform is a real value, what is its phase? Okay, so the Fourier transform capital H1 of e power j omega, this is actually frequency response. It is real valued. We have seen that it is also real and even. It is real for, so if for a real number, what is its phase? Yes, we just have a real value. Let's say if this is like this 2.7, this is a real number, it has no imaginary part. What is its phase? What's the phase? I am asking, what's the phase of this if this is a real value, let's say 2.7? Come on, this should not take you much long. So this is 0, right? So the phase of a real quantity, real number, real value is 0, because you can also write this 2.7 as 2.7 times e power j theta with theta as 0, right? So our theta will be 0, the phase will be 0 for any real number. Okay, all right. So therefore this Fourier transform, since it's real valued, has 0 phase. Okay, this has 0 phase. Now, so if any step is not clear, you can respond and mention your queries. So now initially, remember, we assumed this, we shifted this original impulse response by 2 samples to the left and got our h1 of n. This was our initial assumption, right? Now if this is true, then this is also true. You just replace n by n minus 2 on both sides. Now if you take the DTFT on both sides, Fourier transform on both sides, you get this, and what do you get on the right side? Yes, so on the right side you will get something of the form capital H1 of e power j omega with some factor, of course, because of that delay. So I am asking, what will you exactly get on the right hand side if you take the Fourier transform?
Whether you will be getting the delay like e power 2j.
It will be e power 2j, but e power minus 2j.
Okay, because of minus 2.
Okay, yes. So this is the delay property. So time delay, basically time delay leads to an exponential multiplication in the frequency domain. So, and we have this. Okay, now h1 of e power j omega, we saw that this has 0 phase. So this part has 0 phase, we already saw. Okay, now if we try to calculate the phase of both LHS and RHS, so it's in product. The right hand side involves 2 products, so the phase gets added, right? So phase of first part plus the phase of the second product, second term in the product, which is this. Now this is 0, this is 0 phase. Okay, so this is, what is the phase of this e power minus 2j omega, first term? So I am asking about what's the phase value of this term, what's its phase, highlighted in red.
It is 2j, 2 omega, sorry, minus 2 omega.
Yes, it's minus 2 omega. Okay, so it is minus 2 omega plus 0 is nothing, so it's minus 2 omega. Okay, so we have now found the phase of the actual frequency response corresponding to the actual impulse response. Okay, so that's it. So all we need to do is, we now need to find the group delay that was being asked in the question. So that's it, we are done. We know the phase response is known to us, and all we need to do now is take the derivative, negative of the derivative, correct? So therefore group delay tau of omega is minus d omega of this, which is nothing but d omega of, we just calculated that it turns out to be minus 2 omega, so it is 2. That's our answer. So you see, this was a bit tricky problem, because in the straightforward approach, the way we started initially, by taking the DTFT directly and then trying to find its phase, turns out to be very tedious job. So instead, we just observe that this impulse response has a particular symmetry, which is even symmetry, only with the exception that it is centered at n equals to 2. But we want an even symmetric signal to be centered at n equals to 0, above the origin. We want it to be symmetric around the origin. So that's why we shifted it by 2 samples to the left to get h1 of n. And then since h1 of n is already a real valued as well as even impulse response, we concluded that its Fourier transform will also be real and even, and I have proved it here. So this is the proof. This was the proof. The rough was proof. So and now, since it is also real, the phase of any real number is 0. Okay, so that's why the phase of this h1 of e power j omega is 0. And now, from our given relation that we used, we shifted it, the original impulse response, and then used the property, delay property of time domain and exponential multiplication in the frequency domain to arrive at the final phase response, and we just differentiated it to get the group delay. That's it. So this is our second problem, and now let us move to the third problem. Okay, all right. So third problem, we have been given a magnitude response for a discrete time low pass filter. Okay, it's an ideal low pass filter, and its impulse response is small h of n, which is what we need to find, and also make an approximate sketch of that impulse response. And it is given that the impulse response is real valued. You see, determine and sketch the real valued impulse response for this filter for 3 cases. Okay, I will just solve one case and you can immediately solve the other cases also. So the group delays for 3 cases are different. For the first part, the group delay tau of omega is 5. Okay, just read the question. If it's not clear to you, let me know, then I will start. All right, so okay, so let's start. First point is h of n, the impulse response is real. It was mentioned. Okay, and the magnitude response is given like this. And by the way, if the impulse response h of n is real, which is the case here, what kind of symmetry does the magnitude response and the phase response have for a real impulse response? This was taught in the lectures. Can anyone recall? If h of n is real, what kind of symmetry is actually followed by the magnitude response and the phase response?
Actually, it will be the function will be sine of pi by 4 omega, pi by 4 n. It will be there.
That's
H of n value.
oh, that's fine. That's fine. That is fine. I'm not asking about that actually. So what I asked is, so if this impulse response h of n is real, so what kind of symmetry does this magnitude response and the phase response have? It was taught in the lectures that
It will be having a even symmetric process, even function.
which one will have even symmetry?
It will be from minus pi by 4 to plus pi by 4. We'll be having a
Exactly. So this figure also, if you see, it's like correct. So minus pi by 4 to pi by 4, it's 1. This is the magnitude response. So clearly this is an even function. This is even symmetry. And it's a property that if the impulse response h of n is real, the magnitude response, which is this, which I have plotted here, is an even symmetric function, and the phase response is an odd symmetric function. So you can just recall your notes or the lecture videos. Okay, so it was taught by sir. So anyways, what Venkat was saying, that's right. He was mentioning about the form of the impulse response. That's fine. Okay, so that is fine. So okay. But you see, the thing is, you can't directly compute its inverse discrete time Fourier transform or IDTFT, because we only know its magnitude response. So for the impulse response to go back to the time domain sequence, we first need to know the complete frequency response, right? H of e power j omega. We only know its magnitude within this range of frequency. So we can't directly use any IDTFT formula here. Okay. So first part, and in first part you see the group delay is tau of omega equals to 5. That's the case. So group delay tau of omega is 5. Now tau of omega is, so that's why, so we are being provided with the information about the magnitude response. If we can also find out the information about the phase response, then we have the complete information. Then we have the entire information about the frequency response. So what is left is to find the information about the phase response. So that's why I am trying to use the formula for group delay, okay, which is minus dd omega of the phase of the frequency response, which is this. So tau of omega is 5. If you just put 5 on the left hand side, you get okay, which is minus 5 omega plus some constant, let's say c. Okay, and now the well-known property that I was mentioning, that since the time domain impulse response is real, the phase I mentioned should be an odd function, and the magnitude, as already seen from this figure, it's an even function. So that's the property. For real valued impulse response, the magnitude response follows even symmetry and the phase response follows odd symmetry. So the phase must be odd. Phase is odd symmetric. Phase must be an odd function. Okay. So by the definition of an odd function, f of minus x is minus of fx. True. So just use that basic formula. So therefore f of minus x, which is the phase of e power minus j omega, is minus of this. Agreed? Because it's an odd function, the phase is odd, and we already found out the phase to be minus 5 omega plus c. So if you put it, so minus 5 omega plus c on the left hand side, you have the phase of e power minus j omega. So minus 5 of minus omega, so that becomes 5 omega plus c, and on the right hand side you have this, okay, minus this. Is this clear? Up to this, is it clear?
Yes, sir.
Okay.
Yes, sir.
Okay, good. So now you can just cancel. So this 5 omega gets cancelled, and c is clearly 0. Now if you put c equals to 0 in this expression for the phase here, minus 5 omega plus c, it becomes basically minus 5 omega. So therefore you now have the phase information as well, which is minus 5 omega. Okay. So now all we need to do is again take the IDTFT. So we have in the previous live sessions we have actually computed step by step the IDTFT, but now what we will do is we will use the known formula. Okay. So alright, so but before that, alright, so this is the phase. This is the phase, and this was the magnitude. We can combine them together to find the overall frequency response like this. So therefore h of e power j omega, which is the complete frequency response, is given by the magnitude times e power j, this is e power j, the phase. Okay. So, and now we just saw that this phase is how much it is, minus 5 omega. So this is nothing but the magnitude times e power minus 5j omega. Okay, all right. Okay, so now for this h, okay, this magnitude part, mod of h of e power j omega, its characteristic has been given here. It is 1 within whenever mod omega is less than or equals to pi by 4, and it is 0 otherwise. So it looks like this. So this looks like this. Wait. It looks kind of like this. It is 1 from minus pi by 4 to plus pi by 4. Let's say this is pi, so this is minus pi, okay, this is, let's say, omega, and this amplitude is, this height is 1, okay. This is what it looks like. And so if you take its, so this is the magnitude response for this kind of a rectangular pulse. Of course we expect a sinc function in the other domain. So if we go back to the time domain by taking the inverse dtft, we expect for such a rectangular pulse we expect a sinc function, and vice versa. So we have already solved similar problems, and it turns out that if you verify it, you can also verify it by doing the calculation. So if you take its inverse dtft, you will find that this is actually sine pi by 4 n by pi n. So it's basically, see here, it's pi by 4 is the threshold, right? This point, this pi by 4 is actually present here. Okay, had it been some omega c, let's say, we would have got sine omega c n by pi n. It's just as simple as that. So this is fine, but in our frequency response we have this magnitude times e power minus 5j omega. So what we actually need is our h of e, this thing, it is actually magnitude, this magnitude times e power minus 5j omega. Now where does this go? What?
It will be sine pi by 4 n minus 5.
Very
Where
good.
we can
Very good. Very good. So it's just a time delay. In the time domain there will be a delay because it's an exponential multiplication in the frequency domain, so it translates to time delay in the time domain. So as you said correctly, we have this by, oops, and similarly this will also get delayed by 5 samples. So this is it. This is actually our h of n answer. So we have solved it for the first part, for tau of omega equals to 5, I believe. And now for the plot, you can easily plot this. So, and this is like a sinc function, it's an even function, right? So why even function? Because sine is an odd function times 1 by pi n minus 5 you have, which is another odd function. So overall it's an even function. So if you plot this, I have already calculated this, so you should get something like this. So this is at 0 to 1, let's say here. Should actually be okay.
So our response will be symmetric about 0 and
Correct.
it goes minus 5 to plus 5, whether I'm correct? Or
Why do you say minus 5 to 5?
actually it's start at 0, it will goes to my 5 will be the mid value, whether I'm correct?
5 will be the mid value. What do you mean? So I'm right now what I am doing is I am actually plotting this function. So what you are saying is actually right. I am plotting this function. Okay, this is the normal one.
Okay sir, okay sir.
So that will be actually symmetric about n equals to 0, and since our actual impulse response is actually a delayed version of that, you can just right shift it by 5 samples. So actually, yeah, you're right. So okay, you can do it. Okay. So let me then directly plot the final one on. Okay, so this will be not n equals to 0, but since it gets shifted, it will be n equals to 5, and you will have it's a decaying sinusoid like this, and I think it goes to 0 here. That's 5, 6, 7, 8, 9, and it takes a negative value here, I guess. And so on, it continues like this, and this peak would be, I believe, 0.25, and same thing. So this value would be something like 0.225. This is like 0.159. This is like 0.075. This goes to 0. This is minus 0.045, so on. And same happens on this side because it's even symmetric. Okay, so this is our H of n. Great. So I have done it for the first part. We have determined h of n as well as made a rough sketch of it. Similarly, you can just work out for the two cases. It's just the same way. So you can similarly solve for B and C. Straightforward. Okay, now coming to the fourth question. Yes, any question?
No sir, I have a small work in about the college. I'm leaving. I will see the later on.
Oh, sure.
Thank
No
you.
problem. Okay. Anyways, let's continue. So we are in the fourth question now. So fourth question, we have two LTI systems given by these frequency responses, The first system has a frequency response capital H1 of e power j omega, the second one has capital H2 of e power j omega. And what we need to show in the first part A is that both of them have the same magnitude function, okay, for all omega. So the mod of capital H1 of e power j omega is equal to mod of capital H2 of e power j omega. They have the same magnitude response, but the group delay of the second filtered is greater than the group delay of the first filter for omega greater than 0. That we have to prove. Okay. So it shouldn't be much complicated. Alright, so in the fourth question and looking at the first part, so let me write it down. So this is the first frequency response of the first filter, first LTI system, like this. Okay, and the second one is given by this. Okay, right, so we first need to prove that they have the same magnitude. Okay, so proof. You can individually compute their magnitudes and then equate them and actually verify that indeed they are equal. That's fine. Or what I am doing is just simply taking their ratios first and then taking the magnitude and showing that that ratio is actually 1, so both their individual magnitudes are equal. So basically what I am doing is I am taking the ratio of these two frequency responses, and from the given expression, if you just take their ratio, it is coming out to be like this. And so this is nothing but 1 plus half. So I'm actually running through this problem a bit fast because it is simple, just calculation based, nothing else. Now I can take the magnitude on both sides. So in the numerator we have 1 plus half cos omega whole square plus minus half sin omega whole square plus, by the denominator we have half plus cos omega the whole square plus minus sin omega whole square this is equal to, if you expand this, you get 5 by 4 plus cos omega, both in the numerator and the denominator, and it clearly gets cancelled. So this is 1. The ratio is 1. Ratio of magnitudes is 1, which of course implies that their magnitudes are equal. So proof. Okay, now we have to prove that they have different group delays actually, or more precisely we have to prove that the group delay of the second system H2 of e power j omega has a greater group delay than that of H1 of e power j omega for omega greater than 0. So let's see. So for group delay, remember again we have to use that formula, minus d omega of the phase. So for that, first we have to find the phase and then take its derivative and impose a negative sign. So for finding the phase, let's try to find the phase. Okay. So we are trying to find the phase of the first system, and the first system was given by this. Its frequency response was given by 1 plus half e power minus j omega divided by 1 plus 1/4 e power minus j omega. Okay. Now you can subtract their, because they are divided, so phases get subtracted. Okay, again I am saying, if any step is not clear, you can just unmute and ask me. Okay, and so this is this. There will be a half. Minus j sine 1/4. Okay, I think it's fine. Now just the individual phases, we can use the tan inverse formula. Minus the imaginary part divided by the real part. Alright, so now in this second term you have, we have this negative sign sitting inside tan inverse in the numerator in the second term, and we also have a negative sign in front of the tan inverse itself. So I can take this, pull out this negative sign from inside the bracket to outside, so minus minus becomes plus. So you get tan inverse 1/4 sin omega by 1 plus 1/4 omega minus tan inverse half sin omega you can also use some shortcut method if you have if you can figure out to find the phase, because it's actually a lengthy process. At least the way I am doing is a lengthy process, but anyways. And now to further simplify this, we can use the tan inverse x minus tan inverse y formula, and so tan inverse x minus tan inverse y is given by tan inverse x minus y by 1 plus x1. So we'll use this. So if you do this, I'm actually writing it a simplified answer. What you get is this. So this is the phase of the first term. Okay. And similarly, in the same way, you find the phase of the second system, and you'll observe that it turns out to be tan inverse minus 7 sin omega by 6 plus 9 cos omega. A very similar form. Now our task is to show that this h2 of e power j omega has a greater group delay than that of h1 of e power j omega. So let's see. Okay, I'm writing the phases again just for better understanding. So this is, we obtained minus 2 sin omega by 9 plus 6 sin omega, and the other phase for the second system we got tan inverse minus 7 sin omega by 6 plus 9 cos omega. Okay, right. And we need to consider in the question, we need to consider for the group delay part, we have to consider omega positive, omega greater than 0. So let's consider, let's say omega from.
So can you please check whether it is h1 of e power j omega is 9 plus 6 cos theta or 2 plus cos theta, 6 cos theta? Sir?
Which one you're talking about? h1
h1 e power j omega value to tan inverse of minus 2 sin omega by 2 plus 6 cos theta or 9 plus omega.
Okay, are you getting 2 plus cos theta in the denominator?
No. Oh, okay, sir, I made mistake. Okay, 9 plus omega.
Okay, you are calculating it parallelly. Good. So anyways, this is just calculation based, so you can verify it in your free time, so later. But I hope you should get something like this. Okay, yeah. So these are the two phase responses, and if you see, at omega equals to 0, what happens to the both the phases? What's the value at omega equals to 0? Yes,
0, sir.
yes, 0. So, and similarly for pi also, both of them vanishes, becomes 0. So I can say that this is, if this is evaluated at omega equals to 0 or pi, it is the same as for the second system, the phase evaluated at omega equals to 0 or pi, and it is nothing but 0. Now let us okay, for the extreme points 0 and pi, we have checked that okay, they are indeed 0 for both the cases. Now let's take some intermediate values like pi by 2, let's say. So if we take pi by 2 and if we try to compute the phase for the first system, so if we try to calculate this h1 of e power j omega at omega equals to pi by 2, you will find that it turns out to be tan inverse minus 2 by 9, which is approximately minus 0.21866, like that. Okay. Similarly, if you do for h2 at omega equals to pi by 2, you will get, so of course you would need a calculator to find this value, and you will get 0.86217. Okay, so clearly you see they both these phase responses started from 0 at omega equals to 0. Okay, both were 0 at omega equals to 0, but as omega was increased from 0 to pi by 2, once omega reached the value of pi by 2, the phase response for first system took the value minus 0.21, whereas the phase response for the second system took the value minus 0.86, so even more negative, you see. So it went more negative for the same omega, which is pi by 2. So you see, and what about the group delay? Group delay is like, you can treat it as a slope, right? Because it's the negative derivative of the phase. So it's the slope of the phase, or the negative slope, you can say. Correct? So here you see the phase of the second system that falls more rapidly, that decreases more rapidly, because it went from 0 to minus 0.86, whereas h1 went from 0 to minus 0.2186. So of course you can see that therefore this has greater negative slope, or not greater, I should say, I mean more negative slope, that's what I'm trying to mean. Okay, and so it's so h2 has a more negative slope, okay, because it falls down more rapidly, but this group delay is again the negative of the slope. So overall it will be like more positive, you see. The second system, it has a more negative slope, but on taking its because tau because tau of this thing is the negative, right? It's the negative of the slope. That is group delay is the negative of the slope of the phase response. So if you compare the group delays, clearly H2 is more positive, right? More greater group delay. Okay, negative of a large negative number becomes more positive, right? So that's the tuition. So therefore H2 of e power j omega, the second system has a greater group delay than that of H1 of e power j omega. This is also proved, okay, for omega greater than 0. Okay, so the first part we have seen now. This was the first part of the fourth question, and in the second part we need to determine and sketch the impulse response as well as the step response of the two systems. So maybe I'll solve it partially and then you can solve the complete problem later in your free time. So let's see, to get the impulse response and the step response, 4B. So 4B for B, let's first try to find the impulse response. Okay, so let's consider the first system. Okay, H1 of e power j omega, it was given by this. Now to find its impulse response, one approach could be taking the IDTFT, that's fine, but instead I think it would be more convenient if we actually use the Z transform. So because we can actually replace this e power j omega by Z to go to the Z domain. And why I am talking about moving to the Z domain is that, so what I am doing is I am just replacing e power j omega by Z. This is same as h of z equals to 1 plus half Z inverse by, so basically here I am trying to find what is the impulse response H1 of n for the first system. Okay, so this, and I can split this as two summations like this. Okay, this is H1 of Z. Now see, this form looks familiar. It's a sum of two terms, H1 of Z, and these two forms we have already seen before while discussion of the Z transform, and we know how to go back to its like the time domain sequence from this Z domain. The inverse Z transform we already know, but still for clarity I am writing it. So if you have like this in the Z domain, then let's say and of course the underlying assumption is that the ROC is this, mod Z is outside a circle of radius A, mod A. So, or in other words, it's a causal sequence. The assumption is causal. It's a causal assumption again. If this is the case, in the time domain sequence, on taking its inverse Z transform, it goes to a power n u of n. This is known. We know this. And we will just use this here. So what happens to this first term? So this first term, what I mean is this. Can you tell me what happens to the inverse? Yes.
1 by 4 power n u of n.
Minus 1 by 4 to the power n,
Minus
right?
1 by 4.
Yes,
Yes, sir.
yes.
Minus 1.
Okay. And what happens to the second term?
N minus u of n is 1.
Yeah.
by-
So you see in the second term actually you wait, where is the marker? Okay. So in the second term you see here the constant factor is nothing to worry about, it's just a half. It will be present as it is. We only have a multiplication by Z inverse. So in the Z domain, whenever we have a multiplication by Z inverse, it translates to a delay in the time sequence, which is, if initially you had x of n, you will now have x of n minus 1 because you have a multiplication by Z inverse. If you had multiplied with Z, then you would have got x of n plus 1 advancement, time advancement. But here it translates to a time delay by 1 unit. Okay. In general, if you had z to the power minus n naught, let's say, then you would get x of n minus n naught, like that. Okay. So this is why actually Z transform helps to simplify. So using this relation, this pair, Z transform pair, we have h1 of n actually equal to, for the first term in the summation, you, as you rightly mentioned, this is equal to this, and for the second term is exactly the first term only, delayed by 1 unit from the property of Z transform. So n minus 1 u n minus 1, like this. And now if you have to sketch this is clearly a right sided sequence. So h1 of n, if you observe it, it is always 0 whenever n is less than 0, because this unit step functions will be 0 for those values. And for n equals to 0 it is 1, for n equals to 1 it is 1 by 4, for n equals to 2 it is minus 1 by 16, at 3 it is 1 by 64. So like this. So, and you would get approximately a graph that looks like this. Okay, so yeah, so this is the impulse response of the first filter or the first system.
So if it is minus 1 by 16, we'll be having in the negative.
Yes, tell me.
They're having h1 of 2 equals minus 1 by 16, sir.
Oh, right. Correct. So at n equals to 2, we have like this, minus 1 by 6. So yeah, and similarly, just you can do it for the h2 also, the second filter also. So just verify. Similarly, verify that h2 of n is half. The process is same. You have to take the z transform and then you can take its inverse z transform by using that relation. Okay, a power n u of n, you should get like this. It's again the same things. See the first term and the second, in the second term in the summation we have just the delayed version. Okay, so that's the and you can plot this also easily. It's fine, it's no big deal. And about the step response, so for the step response, let me also show you just one example for the step response. So now for the step response, now so far we have looked at the impulse response. Now let's look at, just for, let's say for the first system h1, let's look at the step response. So we already evaluated h1 of n in the previous part. It has the form like this. U of n minus 1. Okay, so now what do we actually mean by the step response? So this is the impulse response of the first system. So the step response is basically the output of this system when the input is this step function, which is u of n. Okay, so what actually we need to find is, let's say we denote it by y of n, is basically the convolution, right, of this with the unit step function. Okay, that's what we need to find. So it's like this. We have h1 of n, this is LTI system, and this is y of n. So you can use convolution. You can either do it by convolving these sequences, But another thing is you can also use Z transform, because convolution in the time domain translates to multiplication in the Z domain, right? And it's of course easy to deal with multiplication rather than convolution, right? So if we go to the Z domain, this, okay, by the way, I was using y1, right? Y1. Okay. If we go to the Z domain, y1 of Z should be the product, right? Because convolution translates to multiplication. So if I assume that the Z transform of h1 of n is capital H1 of Z, and I denote, let's say, the Z transform of un by this Z transform like this, and instead of convolution now we have multiplication.
Sir, can we use graphical method to find the convolution, sir?
Sure, anything is fine.
The direct, because we have the output of h of n here,
Hmm.
and u of n is a step function, so we'll be having the amplitude as 1, right? If it is a unit step function, so directly can be convoluted
Sure,
or
whichever method you are convenient with. So as a good exercise you can solve it by that method. Okay, now I am solving using this Z transform method, and now you parallelly solve using that graphical convolution method, and then just try to verify whether you are getting the same answer or not. So that's a good exercise. So of course you can use graphical convolution, which is more convenient in this problem. So I would encourage you to just check that. So good. So you can try that. But if you do like this, you should get this is the h1 of z. It's fine, it's already known to us. And the Z transform of the unit step function is basically 1 by 1 minus Z inverse, because basically it's like a power n u of n, a power n u of n with a as 1. So it's basically 1 by 1 minus a Z inverse. So it's 1 by 1 minus Z inverse. Okay, so that's the thing. So yeah, so basically y1 of z is this. Now you can use partial fraction, but I think in this problem, that graphical convolution method is more convenient. I think that would maybe give us the solution in less number of steps. So you can try that. So this you can use partial fractions. So this residues a and b, let's say I can write this. Then if you solve, verify that y1 of z is this. So basically a is minus 1 by 5 and b will get 6 by 5 like this. And now again it's just the inverse, using that inverse relation. So you have this plus this, and you can easily plot it also. And okay, similarly and as an exercise verify the answer using convolution. Okay, so now just quickly moving to the last part of this question. So we need to show that this frequency response of the second system can indeed be expressed as some g of e power j omega times the frequency response of the first system, where this g of e power j omega is an all pass system. And remember, when all pass filters were discussed in week 9, we saw that its magnitude response is 1 for all frequency. It has unit magnitude response. So we are looking at 4C. So see, we don't need to actually do anything for this part, because we have already solved this in the part A itself. Because in part A you see that we saw this magnitudes of H1 and H2 are equal, so their ratio is also equal to 1. The magnitude ratio is also 1, so which is nothing but this g of e power j omega, right? So hence g of e power j omega by definition has to be an all pass filter with unit magnitude response. So it's like a consequence of this part A, 4A. But anyways, for clarity I am writing it. So it's actually already done in 4A. Okay, so we saw that we proved this. And if I take the ratio, but now H2 in the numerator, this I can do, and I can do only if magnitude of H1 of e power j omega is not 0, and you can actually check that it is not 0. You can divide it by H1 of j omega if it is not 0, and it is the case. So this magnitude is not equals to 0. That's why we are able to divide by 8 on both sides. And so this is our actually g of e power j omega as given in the question, which is this. So g is h2 by h1, right? So this for all omega, and thus we have proved this is an all pass system. Okay, and now just quickly look at the last problem. Last problem is very easy problem. So this is the last problem for today. It's a 3-point symmetric moving average filter. So I of n is the output, and so we have scaled multiples of the delayed input, the current input, as well as the advanced input, right? So, and in the first part we have to find the frequency response h of capital H of e power j omega as a function of these a and b. Okay, yeah, so equation 1 shows the input output relation. So all you need to do for finding h of e power j omega is just take the DTFT on both sides, that's it. Similarly, this is a LCCD, right, linear constant coefficient difference equation. So in Z transform also you solved equations like this. So you took it Z transform on both sides and then you found h of z, right? So similarly you need to find h of e power j omega, same thing. So let's do that quickly. I will go through it. So y of n is given by a times x of n minus 1 plus x of n plus a times x of n plus 1. Okay, and if you take DTFT on both sides, you get a times, and remember, so it involves a delay. So in the frequency domain you will have exponential multiplication e power minus j omega. Okay, and remaining is e power j omega. The thing is, if you have x of n minus n naught, that goes to e power minus j omega n naught times x of e power j omega. This is the relation that we have used here. So, and the second term is just simple, it's x of e power j omega, and for the last term we have a times, so it's an advanced signal, so we have a times e power j omega times x of e power j omega. And now we can just divide by x of e power j omega, and this ratio is nothing but the frequency response h of e power j omega, and it is given by b times a e power minus j omega plus a times e power j omega. And you see it takes a very nice form. So this you can pair up, right? This a e power minus j omega plus a e power j omega, it is nothing but 2 times a cos omega, because cos omega is e power j omega plus e power minus j omega by 2. So what you get is this. Okay, so we have indeed expressed the frequency response in terms of a and b. Okay, now in the second part we need to find the scaling factor b of the input output equation. We need to find b such that this frequency response has unity gain at 0 frequency, that is at omega equals to 0 it is equal to 1. Okay, we have to find the b such that this is true. So basically what we are given is this: at omega equals to 0 is unity gain. So just put this, so b times 2a cos 0 is 1, this is 1, so d is nothing but 2a plus 1. Great. So now on the last part. So in the last part, so it's it says that the common choice for the value of a in various time series analysis problems is a equals to half, and for a equals to half we then need to determine the frequency response, that is h of e power j omega, and also sketch it. It is very simple. So in part C, basically a is half. If a is half, therefore b is, we already related b in terms of a, so b is 1 by 2a plus 1, so b is 1 by 2a plus 1, which is 1 by 1 plus 1, which is again half. Okay, so we will put a equals to half and b equals to half in the original expression of frequency response here, b times 2a cos omega plus 1. So doing that, we get the frequency response as b times 2a cos omega plus 1, which is b is half and a is also half, so 2a becomes 1, this, and you can also actually simplify this, you get cos square omega by 2. Okay, and of course it's a real valued frequency response, and if you plot it, square of cosine, so if you plot this h of e power j omega, which is basically cos square omega by 2, at omega equals to 0 you get 1, at omega equals to pi it drops to 0, at omega equals to 2 pi it is basically minus 1 square, which is again 1. It's like this, so it drops like this and again rises like this. Okay, this is between 0 to 2 pi the frequency response goes like this. So that's it for, I think, yeah, so all 5 questions has been discussed. I went a bit too fast in the end, I apologize for that, but yeah, and for that problem you can try out the convolution method also. And if you have any queries related to the assignments, I think assignment number 9, you can drop me an email. So yeah, I think we can conclude for today. I think we can stop now. Okay.
Okay, sir. Thank you.
Thank you for the participation. I'll stop the recording.